Welcome to this lecture in PHAY0031. Today we're going to talk about microscopy. Now, I normally start my lectures by saying, if you haven't already, go and get a cup of tea, come back, and then we'll start the lecture. I normally have a cup of tea, but as you'll notice, because of lockdown in fact, I'm having to record in the school, and so I'm in a microbiology laboratory, and therefore I'm not allowed to have a cup of tea. But you can. So, you get a cup of tea, I'll be sad. When you come back with a cup of tea, press play and let's begin the lecture. What are we going to talk about in today's class? Simply, I need you to understand 5 different types of microscopy. That's light microscopy, which you've probably experienced before, hot stage microscopy, which is a derivative of light microscopy, as we'll see in a moment, scanning electron microscopy, atomic force microscopy, and transmission electron microscopy. So at the end of the lecture you should be able to explain the basic principles how each one of those microscopies work, and also you should be able to give pharmaceutical applications of each type of microscopy. So you should be able to look at an image and know which type of microscope made it, or you should be able to look at a sample and say which type of microscope you might want to use to image it. So the first thing is, what is microscopy? And I'm sure you're aware it simply means imaging a sample and imaging in such a way that it becomes a lot bigger so that we magnify that sample and we can see small details as part of it. Why do we use microscopy? It's simply because many medicines are complicated structures. They might have very porous structures, or they may have lots of different components, and so visualising a sample is a really good way of trying to understand what is where. It's quite hard to do with any other type of analytical measurement. Those measurements typically tell you what's in a sample but not where it is, whereas imaging allows you to say for certain, yes, I've got lumps of drug in a polymer, for instance, or yes, I've got a porous structure. You can't really tell that any other way. The word microscopy itself derives from Greek, as a lot of these words do, and the basic word is micros, which means small, and scopio, to look at. So it means looking at small things, which is very appropriate. Microscopy itself has actually been around for quite a long time, and although it's not clear who invented the first microscope, the first person to use microscopes was a guy called Antony van Leeuwenhoek. So he used a small piece of glass, a little glass sphere, and through that sphere he could actually magnify water droplets, and he could see in those water droplets little things moving around, and so he actually managed to identify protozoa and bacteria. And for that reason he's often known as the father of bacteriology, and there is a journal named after him which is still publishing to this day, called the Antony van Leeuwenhoek Journal of Microbiology, for instance. Now, although his system was very simple, it was just a glass bead, he could use it to magnify things up to 400 times, which at the time was a simply amazing level of detail that you couldn't see otherwise. Of course, a modern microscope is very different from the sort of thing that he used. It's much more complicated than just a glass bead, for instance. But the basic principle of a modern light microscope is actually the same. All the microscopes we're going to talk about, they illuminate the sample in some way, and then they focus that light after it's interacted with the sample so that you can see an image. All these microscopes contain a number of things which have common features. So one is an irradiation source. If you're going to use light to illuminate your sample, you must have an irradiation source, which is where it's coming from. In a light microscope, that is obviously a light bulb, but when we talk about electron microscopy, as we'll see, that's a different type of light source. And I should point out at this point, an atomic force microscope works on a completely different principle. So light microscope, electron microscopes, they work by illuminating a sample, bouncing the light from that sample, and then looking to see what's happened. Whereas an atomic force microscope is working on a fundamentally different principle. It's effectively putting a probe across the top of the sample. So bear that in mind. Atomic force microscope is going to look at right at the end. It's a different type of microscopy. Electron microscopes and light microscopes operate the same way. So they have an irradiation source which is providing the light to illuminate the sample. They have a condensing lens. So a condensing lens takes the light that's coming from the light source, which can be going in all directions, and the condensing lens focuses it in some way. It might create a collimated beam, so that means a beam which is vertical. All of your photons or electrons, depending on which type of microscope we're using, are going in the same way. Or it might focus the beam onto the sample in a very small focused spot. We'll look at some examples in a minute. Then that light interacts with your sample in some way, typically either transmits through the sample or it is reflected back off the sample to an objective lens, and that objective lens refocuses it back to your eyepiece, and then the eyepiece is what you look through to image the sample. I should also say here that if you're using a light microscope, you can look at the sample through the eyepiece, and that's fine. If you're using an electron microscope, you're not going to use a conventional eyepiece because you don't want the electrons bombarding your eyes. You'll be blinded. And so they have a different way of visualising the sample, which we'll look at in a moment. You're probably most familiar with a light microscope, so that's the one that we're going to look at first. So on the screen in front of you is a diagram of a typical light microscope, and you can see the features that I said already. That's a light source, a condensing lens, an objective lens, and the eyepiece. In this particular instance, there are two light sources on the microscope. One is underneath the sample and one is above the sample. So the one below the sample is for transmitted light. So if your sample is thin or your sample is opaque, you can have a light source below the sample. The light will come up, it will go through that sample, and it can carry on to the condensing lens and then to the eyepiece. If your sample is very thick, or it's solid, or it's coloured, so it won't allow light to pass through it, you can't use the light source underneath because the sample itself will block the light. And so you have a light source above the sample, which is called an incident light source, and that light will come down and reflect off the sample to the condensing lens, and then you can view it through the eyepiece. It's quite important that when you're preparing your sample for a microscope that you prepare it in the light of how the microscope is actually using. So for instance, quite often, I'm sure you're aware, you might slice a sample in thin layers before you image it, and that's simply because you want to use transmitted light and it won't go through a thick sample. Or maybe you're not interested in the surface of the material, you're looking at in the core, and so if you have a light underneath it and the sample's too thick, you won't see anything. So you've got to prepare the sample in the right way for the type of microscopy that you're using. Before we look in detail at some examples of how we use these microscopes, I thought it's worth mentioning that you can't magnify an image forever. So what that means is each type of microscopy has a physical limit to the magnification that it can achieve. It's not simply the case that you just keep blowing up the condensing lens bigger and bigger and bigger, and so you could see any structure that you wanted in your material. The physics doesn't work that way. So for each individual microscope, there's a term called the resolving power, which means the limit between two side-by-side objects that can be resolved. What we want is the resolving limit, or R as it's called, to be as low as possible. So the smaller the R value, the smaller the distance between two adjacent things that you can differentiate. So R wants to be as small as possible. For a microscope, R is given by the equation that's shown on the screen. So lambda is the wavelength of light that you're irradiating the sample with, and NA, OBJ, is a funny term. It's called the numerical aperture of the objective lens. Now, you may have done physics at school, or you may not have done physics at school, and so you don't know what numerical aperture is. So, on the slide, there's just a diagram that I've nicked from the internet to show you what the numerical aperture actually is. It's related to the physics of the lens. And essentially, it's given by the equation in the pink box. N is the refractive index of the medium through which the light is passing. I'll come back to that in just a second. Multiplied by sine of a particular angle, and that angle is related to the lens and the light that's coming from the sample to that lens as shown in the diagram. So you can see that the farther away from the sample the lens is getting, the smaller the angle. We want the numerical aperture to be as large as possible to make the value of R as small as possible. So in order to do that, we want the angle to be as large as possible, and we also want the refractive index of the medium to be as large as possible. Again, there are physical limits on the angle that you can achieve with a typical lens. So on the right-hand side of that slide, you can see three different lenses, and the numerical apertures are the maximum that can be achieved. 0.12, 0.34, 0.87 in this case. N is the refractive index of the medium through which the light is passing. So normally that would be air. You'd have your slide underneath the lens, and then between the slide sample and the lens is air. And so normally N you're not changing because it will be the refractive index of air. But it is possible to use media that have a higher refractive index than air. Quite commonly you'd use a mineral oil. And you use a mineral oil because it doesn't tend to dissolve your sample. So you may have seen that sometimes when you use a light microscope. You have the sample sitting on the slide, you have the lens above it, and between the two you actually fill that space with a mineral oil. So there's actually oil touching the lens and the sample at the same time, because that controls the refractive index a bit better through that space. Right, as I said already, we want the resolution to be the highest, and we get the highest resolution when R is the smallest. To do that, lambda, which is the wavelength of light, needs to be small, and the numerical aperture needs to be large. As I said, in air, the refractive index of air is 1, and we can't go higher than that. So the numerical aperture is then fixed by the physics of the lens. And in principle, the highest numerical aperture you can obtain is 0.95, although in reality it'll be slightly less than that. If you switch to a mineral oil, as I said already, the refractive index of a mineral oil is actually higher than that of air. It's 1.6, and so that means we can increase the numerical aperture just a little bit. But there is still a physical limit to what we can achieve with a light microscope. That physical limit, as shown on the slide in front of you, is round about 1,000 times. So with a light microscope, you can take a sample and you can magnify it 1,000 times, but you can't really go beyond that. You're limited by the physics of the lens and the wavelength of light that you're using to irradiate the sample, and there's nothing you can do about it. It's very tempting to think you can just change the lenses in some way, keep putting the light through more and more lenses and it will be fine, but it won't be fine. There is a physical limit to how much you can magnify the image, and for a light microscope it's 1,000 times. Now if you think about the equation for the resolving power of a microscope is lambda divided by the numerical aperture of the objective lens. You can't do much about the numerical aperture, so that leaves you with lambda. And you can't do much with lambda if you're using visible light. But it is possible to use other lights. There are other parts of the electromagnetic spectrum where the wavelength of light can be a lot shorter. And one of those is with electrons. So rather than use photons to irradiate your sample, which you would do with a conventional light source, if you use electrons, the wavelength of electrons is a lot shorter than it is with visible light. The principle of electron microscopy is therefore is that because you're not irradiating your sample with photons, but you're using electrons, electrons have a much shorter wavelength. Because they have a much shorter wavelength, the resolving power of the microscope could be a lot smaller, and therefore the magnification that you can achieve is a lot bigger, typically up to 100,000 times, rather than 1,000 times with a typical light microscope. Now those of you that are following what I'm saying might say, well, how do we focus an electron beam? Because we can't focus an electron beam through a conventional lens. A lens is designed to direct photons, not electrons, and you'd be right. And so the clever bit about electron microscopy is that rather than use an optical lens to change the direction of the electrons, it uses magnets, because electrons have a negative charge, and so a magnet can deflect the path through which an electron is passing. So think about an electron microscope as essentially the same kind of layout as a light microscope. It's just that the lenses have been replaced with magnets and the photons have been replaced with electrons. What that means then is that there are two types of electron microscopy, as shown on the screen, TEM and SEM. The T stands for transmission and the S stands for scanning. The arrangement is exactly the same as we saw for the light microscope. If the electron source is below the sample and those electrons are passing through the sample to the condensing lens, then it's a transmission electron microscope. On the other hand, if the electrons won't pass through the sample, and the sample has to be really thin to let electrons pass through it, so in the majority of cases an electron microscope is set up in the scanning, the electrons are fired at the material from above and they bounce off to the condensing lens, or magnets in this case, and it's a scanning electron microscope. You might say to me, well, if it's the electrons are coming down from above and they're bouncing off the sample, why is that not reflected? Why is it not called reflectance electron microscopy? Because that would be the same as a light microscope. And the answer is that actually the way the experiment is done, the electron beam is focused to a really small point and scanned across the surface of the material. But I'm going to come back to that in just a second. So it's scanning electron microscopy, not reflectance electron microscopy. Okay? Doesn't matter which type you're using, the magnification limit is the same. It's around about 100,000 times. And the reason is because the magnification isn't about how the microscope is arranged, it's about the wavelength of light, which is electrons in this case. There is one issue to think about with electrons and electron beams, and that is if you think about mass spectrometry, for instance. How is a sample put down a mass spectrometer? So the answer is, especially if it's an organic sample, an electron beam is fired at those organic molecules, and that has the effect of breaking them up into small fragments, and those fragments go down the mass spectrometer. So you might reasonably say to me, if my sample is an organic material and I am firing electrons at it from an electron gun, won't I destroy the sample? And that would be a very fair question. And the answer is, you absolutely would do that. You would completely destroy the sample. How then does a scanning electron microscope in particular work? The answer is, we don't allow the electrons to interact with the material, because if it does, it's going to destroy it. So we have to coat the material in some way to protect it. Think about it as a protective coating on the outside that the electrons are going to bounce off of rather than get to the sample themselves, a shield, if you will. And so typically what we use is a heavy metal. And I'm not talking heavy metal like Guns N' Roses, we're talking heavy metals like gold. That's a good heavy metal. It's inert, and so it's sprayed onto the surface of the sample with a special technique called a sputter coater. I love that word, sputter, not splutter, sputter coater. Okay, so that's essentially heating up some gold to atomize it, and then those atoms of gold travel across and they land on the surface of your sample, and they build up a really, really thin layer across the surface of your sample. It's really important that the surface is thin. Can you imagine that if you're trying to image your sample 100,000 times bigger than it actually is, and you cover it with a great big blob of gold, all you're going to see is a smooth surface of gold. You've lost all the detail in your sample. So it's really important that the gold covering on your sample is really, really thin. And that's achieved with sputter coating, because it's literally depositing gold atom by atom to cover up the surface of your material. When you image the material then, the electron beam comes down and it bounces off the surface because it's hitting the large gold atoms and doesn't have a chance to get to your sample and destroy it. Okay? It's really important when you look at an image that's been made with a scanning electron microscope to remember that you're not actually looking at the surface of the material directly. You're looking at the surface of that material covered in heavy metal. Okay? Kind of important to keep that in mind. On the screen in front of you is a setup for a transmission electron microscope. The electron source is at the top usually. It can be something as simple as a heated wire element actually that's emitting electrons. So those electrons are coming off that wire and they go to the condensing lens, which is a magnet, as I've already said. They form a collimated beam. So a collimated beam is a beam where all the electrons are going in the same direction, so vertically down in this instance. Then they are passing through the sample. Your sample needs to be relatively thin in order to allow the electrons to pass through it. If the sample is thick, then the electrons will simply stop, so they will pass through your sample. You might say to me, do we sputter coat a sample for transmission electron microscopy? And the answer is no, because if we did that, the electrons won't go through it, they will actually bounce right back. So for transmission electron microscopy, we don't coat the sample. You might then say to me, isn't there a risk that we will destroy the sample with the electron beam? And the answer is absolutely. And it's very common when imaging with a TEM, you'll actually see your sample start to be eroded because it is literally being shot to pieces by the electrons. So it's one of those things where you can't really put a sample into a TEM and get it back out again. It's very damaging to the sample just making the imaging measurement in the first place. So electron beams pass through the sample, they're then focused with your objective lenses, or magnets in this case, and then, as I said before, you can't look directly at an electron beam to image the sample because it will destroy your eyes. And so what normally happens is the electrons hit a fluorescent screen. The fluorescent screen then produces light in response to an electron hitting it, and that light is then transmitted to the ocular lens. So you are seeing a light source, but the light source is coming from the electrons. So you're not looking at the electrons directly, the electrons are hitting the screen and being converted to light, and then you're looking at the light source. And I suspect that with more modern TEMs, the electrons hit a CCD array, and that image is transferred directly to a computer, and then you're looking at it through the computer. A scanning electron microscope is slightly different in its setup, and there's an image on the screen to show you what that looks like. And the reason it's different, as I alluded to already, is because we don't irradiate the whole sample with electrons in one go. That would be quite damaging for the sample, and also it would mean that the electrons can scatter in multiple directions, and we wouldn't really be able to condense them back towards the eyepiece. So instead, the way that the microscope works is the electrons are fired from a source, as they are from a TEM, and they're focused by a series of magnets, but in this instance, rather than making a collimated beam, they're focused to a very fine point. Okay, so all the electrons are coming down to one point. That point is then moved across the surface of the sample, again by magnets, and it's done in a raster pattern. So rastering means moving backwards and forwards across the surface of the material. So think of it as a single point which is hitting the surface and reflecting off, and then we move backwards and forwards across that surface. So a bit like an old TV monitor, if you've ever seen one of those, which was done with an electron gun, and it's got lines going across it. The image is created in the same way, with lines. And quite often, if you sit at the SEM and you watch the image appearing on the screen, you'll actually see it appearing as a series of lines, because that's the way the image is actually being created. So rastering across the surface of the material. Right, so that's the basic principle of light microscopes and electron microscopes. We haven't touched on hot stage yet, I'm going to come back to that in a minute. And atomic force microscope is completely different, so park that in your mind right now. We're just going to think about those basic types of light microscopy for now. Why are we going to use microscopy for pharmaceutical samples? And there's only one reason, and that is to visualise the sample. A microscope can do nothing else but show you an image of the sample. So you're just looking at it to see what it actually looks like for real. Which type of microscope should you use for a particular sample? The answer is really dependent upon the size of your sample. So if you think about a light microscope, it can achieve a magnification of, say, 1,000 times. So you can put in something which is quite big, say a tablet or a capsule or something like that, and you can blow up the surface of that tablet or capsule, and you can see some quite good features on the surface. 1,000-fold magnification is quite good. SEM or TEM, on the other hand, are blowing up the sample, say 100,000 times, and that's way too much resolution for something really big like a tablet or capsule. You need something a lot smaller. So essentially, the choice of microscope is dependent on the size of your sample, as shown on the table. Powders, tablets, crystals, things like that, large things, are generally imaged with light microscopes because you don't need to go any further than that. You're not looking for really small structures. And as you go down, surfaces, I put micronized powders, micronized because you can make a surface of a material amorphous by milling it, as we talked about in the dry powder inhaler lecture. And so you can also image to see whether something's crystalline or amorphous with SEM. Crystalline materials tend to have sharp edges in an SEM image, and amorphous materials tend to be rather smooth. So you can use SEM imaging to look at a material that you suspect to be crystalline or amorphous, and you can tell whether it is crystalline or amorphous. When you get down to really small structures, so things like nanoparticles or liposomes or even viruses, those are really small structures. And you can use transmission electron microscopy for those because the electrons can pass through those samples because they're so small. On the screen in front of you is a typical example from a light microscope. In this case, it's an emulsion. So the droplets are quite large, you don't need to go to electron microscopy. It's also liquid and moving around a bit, so it's quite handy to just image it quickly with a light microscope. And you can use an image like this to determine how heterogeneous or homogeneous your sample is. So you can see in this case you've got some reasonably large droplets and some small ones. So you might want to homogenise that again to get a better distribution of sizes, for instance, for the droplets. There is one thing to think about with light microscopes, and that is depth of field. Okay, and that's especially true in reflectance mode. So what will happen is you've got a set of lenses that are focusing the light onto your eyepiece, but they don't have the capacity to deal with light that's gone on different parts. So if you've got a sample that's quite thick and it's in reflectance mode, some of that light will reflect off the top of the sample, some might come down and bounce off the side or the bottom of that sample, and the path that light is taking is different. This path is a lot shorter than this path. Now what that means is, depending on where you've got your lenses, the top of your sample can be in focus, but you'll find that the bottom is out of focus. Similarly, if you change the lenses so that you put the bottom of the sample in focus, the top becomes out of focus. So it's got a very narrow depth of field, and you only have one part of your sample in focus at any one time. So that's a little bit tricky. So the images on the screen are showing you the same sample, but with the lens at different positions in that sample. On the screen is an example now of an SEM image. We've looked at these in other lectures, and I said many times you can usually tell an SEM image because it's a grayscale image, as you can see in this case, and you don't have a depth of field issue with SEM. It's not that the issue isn't there. Clearly an electron can take a longer or shorter path depending on where it's hit your sample. It's just that the sample is super thin, and so because it's so thin, depth of field isn't really a problem because your sample doesn't actually have much depth to it in the first place, so that's kind of handy. You can usually tell an SEM image because it's grayscale, and you can usually tell whether the material is crystalline or amorphous, as I said already, by looking for sharp edges or smooth surfaces. Typically we would use SEM for spray dried powders or milled powders, and again we're looking for particle size, smoothness, regularity, that sort of thing. The image on the screen is actually quite an interesting one. It's a spray dried microparticle that contains drug particles. And so one thing you can do with SEM is you can image various parts of your sample. So one drawback of SEM is you're only looking at a very small part of your sample, clearly. So in this case, there's a whole powders that have been spray dried, and we're only looking at one of those powder particles. You imagine there are billions of other ones we're not looking at. So you can move around with the SEM and you can image different particles. In this instance, one of those particles is actually fractured open, and so you can see inside the particle. So I think it's quite a funky looking image, which is why I use it. Although the images are grayscale, it's also possible to use Photoshop or some sort of software to manually colour those images. So that's literally just going in and changing the colour of each pixel. So we used to have a lady that worked at the school that did that. So as you walk around the school and you look at some of the artworks on the wall, when you're allowed back in the school after this COVID thing anyway, you'll see that there are lots of images, multicoloured images on the wall of the school, and they were all taken with SEM and manually coloured. On the right hand side of this slide is a rather wonderful textbook about pharmaceutical isothermal calorimetry. Highly recommend it, it's a really good read. I know the author personally, tremendous guy, it was in fact me. So when I needed an image for the cover of that book, the publisher said, we need a really funky image for the cover. I asked the lady that worked here, Annie her name was, to colour me an image. And so the image on the cover of my own book is an SEM image of an aspirin crystal, and she called it aspirin flower, which I think is rather nice. And we've looked at some images like this before, but essentially this is showing you the difference between a crystalline and an amorphous material when imaged by SEM. So, if the material is crystalline, generally it will have sharp edges. It doesn't really matter what the habit of the material is, it's usually going to have a sharp edge somewhere. So on the left hand side of this slide, you can see lots of sharp edges as the crystal's end, and that is usually an indication that the material is a crystalline. It's not 100% proof, and you really do need to go for X-ray diffraction to convince yourself it's genuinely crystalline, but nonetheless it's a good indicator. Also, you can watch a sample, especially if it's an amorphous sample, it's probably going to crystallise over time. So you could image the same part of that sample over days or weeks, and you might see the appearance of sharp edges, which is an indicator that the material is crystallising. The image on the right hand side of that slide looks a lot different, doesn't it? It looks very porous for starters, and also it's a sphere. And so that was made with a process called spray freeze drying. So we took an inkjet printer actually, and we jetted droplets of that that solution into liquid nitrogen, which instantly freezes it, and then we remove the water by freeze drying. As I think I've said before, freeze drying removes the water by sublimation, and it leaves void spaces where the water was when it turned to ice. And so you can see that structure is very porous because the water had been removed by sublimation. So you can tell a little bit about your sample and how it was processed just by looking at the images with an SEM. This image, which is on the screen, I find quite interesting because it is actually a tablet that has been cut in half. So a little bit difficult to imagine, but it's got a smooth edge and then a sort of rough surface. That roughness is where the tablet's been cut in half. You're looking at it in cross-section. And I said at the start, you wouldn't normally image a tablet with SEM. So why am I looking at an image of a tablet that's been imaged with SEM? And the answer is because in this instance the tablet was film coated with an enteric polymer coat. Okay? And the question that we're trying to ask here is, or answer, is how thick was the enteric coat? So I don't know if you can see this, but if you look at that cross section, in the middle you've got sort of quite a rough powder, and that's the tablet core, but around the edge, I hope you can see, there's a sort of relatively thin line, and that's the polymer coat. And so you can actually measure the thickness of that polymer coat, and it allows you to know how long you need to leave the core in the film coater to get an acceptable enteric coat film. These images are from transmission electron microscopy, just to show you how small you can image with that technique. It's actually kind of frightening. So I think that on the left-hand side we have viruses, actual individual viruses. That's pretty small. And on the right-hand side we have multilamellar vesicles. So those are phospholipid bilayers, and you've got multiple bilayers like an onion, layer by layer. So if you look at those images, you can actually see the individual lines corresponding to individual bilayers. And this image, I've just changed to the next slide, shows you quite how high the magnification you can achieve with a light microscope. So if you look at the bottom, you can see that it's 311,000 times magnified, and again you're looking at individual virus particles. It's really amazing the level of resolution you can get to with a TEM. So before we stop for a coffee break, there are just two more derivatives of light microscopes that I think we should look at. And they're often done in combination. They're hot stage microscopy and cross-polarized light microscopy. So dealing with hot stage first, hot stage does exactly what it says on the tin. The stage of the microscope is heated, usually just heated, but it can be cooled as well. And so what that means is you can put your sample onto the stage and then you can heat it up. And that's really useful if you're doing something to your sample like looking at it melt or change polymorphic form, and maybe you've measured it by differential scanning calorimetry. So you've heated your sample up maybe to 200 or 250 degrees, and you've got a series of peaks and troughs on your DSC trace. And the question is, what is my sample doing with all of these peaks and troughs in the DSC? In a hot stage microscope, you can do the same thing. So if you heated the sample up at 10 degrees per minute in the DSC, you can heat it up at 10 degrees per minute in the hot stage microscope. And rather than measure some sort of phase change, you're just looking at the sample. So for instance, if you say that in the DSC, this particular endotherm corresponds to melting, then when you look at your sample in a hot stage microscope, you should see it melt at that temperature. If it doesn't melt at that temperature, you know you've misinterpreted your DSC, for instance. Okay? So it's a very useful technique for running alongside the DSC. You can match the heating rate, but you're actually looking at the sample to see what it is doing. So that's quite a good technique. So that leaves us with cross-polarized light microscopy. Now don't worry about what cross-polarized means, I'm going to come on to that in a second. First we talk about what polarized light means. So on the slide in front of you is a diagram that is meant to show you what happens with a polarizing filter. So a polarizing filter is really a diffraction grating, so that means it's got a grid with all the grid lines in the same direction. So imagine my fingers are the diffraction grating, and below my hand there is a light source which is releasing photons. The photons travel in waves, and those waves have a particular plane. So it might be this plane, but it might also be this plane. So those photons leave the light source and they approach the grid. Only the photons that have got the same plane in orientation with the diffraction grating can pass through. So in this case, photons doing this can pass through my grating, but any other photon in a different plane gets stopped by the grating. So the light on the other side of the grating, all of the photons are travelling in the same plane, okay? Which is meant to be represented on the left-hand side of this diagram. Photons in all different directions below the grating, photons all in the same plane after the grating. The reason it's called cross-polarizing microscopy is because we have two gratings, one at the bottom and one above the sample. So this grating is before the sample, this one's after the sample is sitting in the middle. If we had no sample, so there's no sample showing on the first two images on this slide, then what would happen is the light is polarised as it goes through the bottom filter. If the top filter is exactly the same orientation as the bottom filter, the light can pass through both. And so we will see light beyond the second filter. If we rotate the top filter so that now the grating is in a different orientation to the bottom, the photons, when they get to the top, will get stopped because they're not in the same plane as the diffraction grating, and we'll see nothing. So if we just have two filters and we rotate the top one, there's one orientation when we'll see light, and every other orientation we won't see light because they don't line up. So the principle of cross-polarized light microscopy is that some samples are capable of rotating light. In other words, plane polarized light arrives at the sample, it interacts with that sample, and when it comes out it's in a different plane. Okay, so what that means is we have a diffraction grating below the sample, we have the sample, and then we have another diffraction grating on the top. So what we need to do is rotate this top grating as we have our sample being illuminated by plane polarized light, and we rotate it until we can actually see some light from that sample. And it may not be that the two gratings are the same because the sample is rotating the light. Why is this useful at all? Because it sounds theoretically boring, doesn't it? But the answer is because crystalline materials are able to rotate plane polarized light. Amorphous materials are not. So right there, you've got a way of differentiating between crystalline and amorphous materials. Even better, crystalline materials tend to, because they have a mixture of different crystal sizes and shapes, for instance, if it's a powder, they tend to produce a multicoloured pattern. It's called Birefringence. So when you look at a crystalline material through cross-polarised filters, you often see a rainbow colour of effects as shown on the image on the screen. Whereas if you have an amorphous material, because there's no repeating pattern, that the light is essentially scattered in all directions and so can't pass through this top filter, and therefore an amorphous material appears black. Now I said, if you use this in combination with hot stage microscopy, you really can start to interrogate samples that you've studied by DSC. So let's think the sorts of questions that you might ask by DSC. Is my sample amorphous or crystalline? Does it melt? Does it recrystallise? Does it go through multiple polymorphic forms before it melts, the highest one melts, or whatever? You might have a whole series of peaks and you don't know what they correspond to. If you use a hot stage microscope, you can mimic the heating process of the DSC. But if you conduct it with cross-polarising filters, you can also say, is this material crystalline or amorphous? And even better, if it goes through multiple crystalline phases, the birefringence pattern will change. And so it's really easy to say, absolutely, this is going from one crystalline phase to another because the pattern of light is changing. So it's a really common and really useful technique to help you interrogate samples alongside the DSC. Right, so what that means is we've looked at light microscopes and electron microscopes, and they're basically doing the same thing. One's using photons and one using electrons to illuminate your sample. One's using lenses to focus the light and one's using magnets, but the basic principles of those techniques are the same. So what we're going to do is we're going to have a coffee break, and when we come back we're going to look at atomic force microscope because that operates on completely different principles. So, go get a cup of tea and I'll see you in a bit.